Hey everyone. So the next unit we're going to be studying is on simple harmonic motion, or periodic motion, or sinusoidal motion, all names which will apply to what we're looking at. Um, in particular, what we're studying are springs. Okay, springs have some interesting physical properties that are unlike other materials because when you stretch a spring or compress a spring, it always bounces back to its original position. So this applies to springs or elastics or anything like that. So this piece of unit is meant to tie together the work that we just completed on energy and tie it into our next unit on waves. Okay, but before we jump right into examining springs themselves, let's take a look at this simulation here. Here we go. Just let me remove my unchecked. So here we have a spring, and we have a couple of masses down below. So I can take, for example, the 100 kilogram mass and attach it to the spring. And when I do, the spring is going to stretch. Okay, it's going to stretch past its original position. So this blue line, unstretched length, this blue line represents the original position of the spring. Okay, I'll stop it from moving. And now it's at a new resting position. Okay, so something we know right now, the object is not moving. So the spring is standing still. So we know it's an equilibrium or that all of the forces are equal. Okay, its net force is zero here. In particular, the forces acting on this object right now is we have force of gravity acting down, and we have the spring force, or what we call the restoring force, acting back up, trying to pull the spring back into its original position. Okay, some things we can change about a spring. Um, if we increase the mass, of course, the new resting position is going to go lower, okay, because the mass pulls the string more. Same as if we decrease, it goes less. So back to 100. The other thing we can change is the strength or the thickness of a spring. So is it a really thin, easy to move a spring or a really thick spring? So by changing that, again, by making it larger, we shrink the amount or we shrink the how much the 100 kilogram or 100 gram mass can change the length of the spring or stretch it. If we decrease it, just the opposite, we make a really easy to move spring. Okay, so we're going to study the math behind all of this and also the math behind these oscillations. Okay, and how we can use these oscillations to determine things like the uh, spring constant or the period of a spring or how much mass a spring can hold before it may break. So we'll come back to this simulation in a couple of minutes. But first, let's start looking at a couple of spring laws. So let's picture a stationary mass on a spring, just like we did in a second ago in the simulation. So the force is on this spring. We have our force of gravity down, and we have our spring force, which we call F of S, or our restoring force, going directly up. Okay, the net force here is zero. So if we add the two forces together, they have to sum to zero. They cancel each other out. Now we already know our equation for Fg is mass times gravity, but Fs, okay, Fs, which we call the restoring force, is equal to minus kx. X here is the distance that the spring is pulled down from its initial position, and k is what we call the spring constant. And we'll get back to that in a second. But this whole equation, Fs equals minus kx, is called Hooke's law. The reason why the negative sign is there is because if we pull the spring down, making our x negative, the spring force acts in the opposite direction. So the spring force pulls it back upward to its initial position. So the negative is there to cancel out the sign of the s, because x and fs should be different signs. Force of gravity, as normal, is mass times gravity. Okay, so the restoring force that's exerted by a spring is linear. Okay, and we'll see what a graph of that looks like in a second. But our equation is F equals Kx. So you know from math, a linear equation, right? Y equals mx plus b. So if we assume our b to be 0, our y here is just our spring force. Our x is, well, still our x, our distance, and our m, or our slope, is equal to our spring constant k. So it is a type of linear equation, just kind of in disguise here from how you'd normally see it. So x, or k, sorry, is the spring constant, and it's measured in newtons per meter. Okay, and the spring constant, although it's a constant, it is a constant for one particular spring. Two different springs will have different spring constants. Okay, now measured in newtons per meter, or a force per distance. So let's take a look at that for a little closer for a second. So K is equal to our spring force, or our force over our change in distance. So from this, we can see that K is proportional to the force that's applied. So what this means is that when K gets bigger, okay, the larger K is, the more force it takes to move that spring. So if we have a spring constant of 30, that means it requires 30 newtons to move a spring 1 meter. So again, the larger K is, the more force that's needed to pull that spring. K is inversely proportional to the distance. So what that means is the more distance that we can move using a particular force. If a force of 1 lets us move really far, we'll have a small spring constant. Whereas if a force of 1 only moves the spring a tiny little bit, we'll have a very large spring constant. So the easier it is, or the more distance a spring moves, so the bigger x, the smaller k. Actually, before we move on to this next example, let's go back for a second and take a look at our simulation. Do a little calculation. So let's take out this ruler here for a moment. So we're going to look. Here is our initial position, of our spring. Okay, we're going to take the 100-gram mass. Let's do a quick calculation of the spring constant of our virtual spring here. So if we take our 100-gram mass and stop it at its equilibrium, so it drops it down, you can see about 20 centimeters. So we've taken a mass of 100, and we have an x, or our change in distance, is from 0 to 20, so our change in distance is 20 centimeters. So we know the distance, we know the mass, so from this we should be able to calculate the spring constant for this spring. So let's go back and try that. Here we go. So the distance we moved, or x, since the distance is down, we'll call it negative 20 centimeters, or negative 0.20 meters. Okay, the mass I hung on the spring was 100 grams, but we always want our masses in kilograms. And our goal here is going to be to find K. Let's draw a free body diagram for our system. Force of gravity down, and we have spring force up, or spring force, or also known as restoring force. So since it's not moving, we know those two forces have to be equal. Fg is equal to our Fs. Okay, so let's calculate Fs, because if we know our spring force, we can then calculate K. So Fg is mass times gravity. Mass is 0.100 times 9.8, or we get a spring force of 0.98 newtons. Now from this, we can use our equation. Now the spring force is up, so it's positive. So F of S is equal to negative Kx. Okay, so we have 0.98 is equal to negative k times negative 0.20. And from that, we get a k, if we rearrange and divide by our 0.2, we get a k of 4.9 newtons per meter. So this virtual spring requires 4.9 newtons of force for every meter that you want to move it. So let's try another example here. So a piece of rubber, it's 45 centimeters long when a weight of 8 newtons hangs from it, and is 58 centimeters long when a weight of 12.5 newtons hangs from it. An important thing to remember is that weight is not mass, right? Weight is equal to our force of gravity. So this is saying our force of gravity is 8. If we wanted to find the mass on this, we would have to take our force of gravity and divide it by 9.8. Okay, so when a force of 8 hangs from it, the piece of rubber is 45 centimeters long. So as force is hanging from it, that means from here to wherever this mass is. So here's our piece of rubber. This length is 45 centimeters. Now, we can't directly calculate our spring force or our spring constant from here because we don't know the original equilibrium position of our rubber band. We don't know its original length. We only know the stretched length. But conveniently, we have two pieces of information here, and we know that the spring force equation is a linear equation. So let's see how we can solve this. So we have our x1 is equal to 45 centimeters, which is 0.45 meters. And we have our force that was applied to that is 8.0 newtons. We have our x2, which is 58 centimeters, which converts to 0.58 meters. And our force 2, which is equal to 12.5 newtons. And we're looking for our value of k. Okay, again, we know k is the slope. So if we have our equation up here, Fs is equal to minus kx, we know that this is the slope. If we plot a graph of our force versus our distance, we will get a slope of k. Now remember, to calculate slope, rise over run, we just need 2 points, and conveniently we have 1 point here and 2 points here. So let's just graph our points on a line. Okay, so here's a graph of force versus distance. This chunk here, it doesn't cross directly through 0, so this would be the original length of the rubber band. We could find it if we wanted to. We're not interested, so we won't worry about it here. But that is what that length represents. So let's take a look. What do we need? We need our change in y, because we need to calculate our slope. Change in y is just equal to our change in our force, which is force 2 minus force 1, or 12.5 minus 8.0, which gives us a change in force of 4.5 newtons. Then we can get our change in x is, well, it's our change in x, which is x2 minus x1, which is 0.58 subtract 0.45 to give 0.13 meters. And lastly, we can calculate k. So by rearranging the equation at the top of the page there, we can get k is equal to our force over our distance, or since it's a slope in this case, our change in force over our change in distance, 4.5 newtons over 0.13 meters. And that gives us a spring constant of 35 newtons per meter. And again, what that means is it requires 35 newtons of force to stretch this rubber band 1 meter. Here's a practice problem to try. So the spring in a typical Hooke's law apparatus has a spring constant of 15 newtons per meter and a maximum extension of 10 centimeters. What is the largest mass that can be placed on the spring without damaging it? Okay, so take a minute here, try this practice problem on your own, pause the video, and then come back to it in a couple of minutes once you've given it a shot. Okay, so writing down our given information, we have a spring constant of 15.0 newtons per meter. We have an x value, or a change in distance, of 10.0 centimeters, which is 0.100 meters. And we're looking for the maximum mass we can hang from this spring. Start as normal with our free body diagram in this case. Fs or Fg going down. They're equal and opposite. We have our K and our X, which means we can find our spring force since we have our K and our X. So since it's stretching, let's assume that the X is in the negative direction and it's stretching down. So we put our negatives here. We have our equation Fs is equal to negative Kx, which is negative 15.0 times negative 0.100. Since f of s is up, we want our x to be down, and that gives us 1.50 newtons. So this is the force that requires it to hang at equilibrium, where everything is in balance. We know that f of s is equal to Fg, because there's no net force, it's not moving. So here we get mass times gravity is equal to 1.50 newtons. Our gravity, this means mass times 9.8 is equal to 1.50, and we get a mass of 0.153 kilograms. Okay, since we used the maximum distance that the string can stretch, this calculates our maximum mass that we can put on the spring before the spring will get damaged. Okay, so that brings us to the first section on Hooke's law. Okay, now we're going to jump into some material on simple harmonic motion. So the next thing we're going to look at is what happens when we start to move a spring or have a spring oscillating around a particular point. So first, let's start with a horizontal spring. So here we have a spring resting on a table. We'll assume the table is frictionless. Okay, it's resting at its, we put a block on it, it's resting at its equilibrium position. So in this position, we know that the net force on the block is equal to 0. Okay, 0 newtons. It's not moving, just sitting there. Then what we can do is we can apply a force. Okay, we can move that block away from its initial position. So we move it in the positive direction, some value of x, some distance x. Okay, when we move it, what happens is because the spring is now stretched, a spring force is created. Okay, that spring force tries to return the block to its original equilibrium position. So in this case, our net force on the system, okay, is equal to our spring force. Since we ignore friction, spring force is the only force there is, which is going to be equal to negative Kx. Since our x is positive, our spring force will come out as negative. It tries to bring it back to that 0 line. Once it comes back to the 0 line, it's going to keep going because it's going to have some momentum at this point. So its inertia is going to keep it going past the 0 line to the left over to this side. So now the object has moved some distance, negative x to the left, and this spring force is going to try to now push it back to the right, um, and we get, again, our net force equation is Fs is equal to Kx. Since our x is now negative, the two negative signs will cancel out, giving us a positive value for our spring force. So an important thing here is the spring force always acts toward the equilibrium, resulting in an oscillation. So if we think about the size of the spring force here, when it's at its maximum points, is what we can call x max out here. Okay, that is when the force is the largest because the spring is stretched or compressed, okay, as much as possible. So the force is going to be large when it's near its equilibrium position. So as the box approaches the middle here, the force is smaller. It doesn't need quite as large as a spring force to get it moving to that equilibrium position. So the force does change throughout this course of oscillation. Okay, so oscillation is considered simple harmonic motion if the restoring force is linear. So we said the force changes, but if it changes in a linear way, then we consider it simple harmonic motion. And the position oscillates following a sinusoidal pattern. Okay, where the height of these waves here is equal to the amplitude. The period is from one wave crest to another wave crest. This should be familiar to you if you've looked at the graphs of sine waves in math class. Okay, so all the same principles that you do in math apply to here. The only little bit of a difference is we use, because the spring, if it's a vertical spring, okay, the box is bouncing up and down. The amplitude, or how high it bounces up and down, we call x. Okay, and that's on the y-axis is its displacement. And the x-axis is time. So this is just graphing how this spring bounces up and down through over a period of time. So a little bit about period and frequency before we move on. Period is the amount of time required to complete one revolution. So imagine here for a second that you are on a Ferris wheel. Okay, and you are standing, not standing, you're sitting at the top of a Ferris wheel. So the period is how much time it takes for you to be at the top, to go around one full revolution, and be back at the top again. Okay, so that is the period of motion. We call that one cycle. So it's the amount of time to complete one cycle. Frequency is like the opposite. Frequency is how many times you go around in 1 second. So on a Ferris wheel, you might go around a fifth of a time, or a quarter of your motion in a second. Hopefully it's not too fast, you don't want to fall off. Period is measured in seconds, and frequency is measured in hertz, which is actually equal to 1 over a second, which we call a per second. Okay, we can relate frequency and period together. Period is equal to 1 over frequency, or frequency is equal to 1 over the period. We can use both equations. A second equation, which we usually apply to frequency to calculate it, frequency can be calculated by looking at n over time. And what n is the number of cycles of motion. So for example, if you time yourself to go around that Ferris wheel 10 times, and it takes 5 minutes to go around 10 times, that means your frequency, we would put 10 on the top for 10 cycles, and the time would be 5 minutes, so we would have 2 cycles per minute, or 2 hertz. So now we're going to take this idea of period and frequency, but we're going to look at it in vertical motion. So in vertical motion, we have the spring hanging down. We now have the effect of gravity at play. So our initial position, A, is our original equilibrium. We call that our 0 point. Okay, so this is the point. Nothing's hanging from the spring. It's just sitting there. B, we attach a mass, and we allow it to come to rest at a new equilibrium. So at B, the net force is 0, so we know we have our force of gravity down, and we have our spring force up, and they are equal and opposite. So since the net force is 0, we know that the force of gravity plus the spring force is equal to 0. Okay, or mg minus k x naught, that's our new equilibrium position. So here, that's equal to 0, or we know that mg is equal to kx naught. So this is true for our new equilibrium position at B. Now in part C, what we've done is we've applied a force. So we've applied a force to stretch that box down, and then we let go. And what will happen is when we let go, that box will start to oscillate up and down around a new position. Okay, so if we think about it now, since it's moving, we are going to have a net force. So now we have our net force is not 0, so we have our new equation. Net force is equal to the spring force plus the force of gravity. So we can start making a few substitutions. So spring force, so we have to look at our total distance moved now, which is from 0 all the way down to the bottom. So it's k0 plus, or sorry, x0 plus x is our total distance that we've moved from our 0 point. X plus x0 plus mg. Now from up above, we saw that mg is in fact equal to kx0. So if we substitute that, plus kx0, and we expand this first term, we get minus kx kx0 plus kx0. We actually see that the gravity term cancels out. There is no more gravity in our equation, and we just get left with the net force is equal to the spring constant times that new distance x that you stretched it from the new equilibrium point. So we don't actually, we can ignore gravity in this case when we're looking at an oscillating spring or an oscillating mass on a spring. So this is the same equation that we would have used for the horizontal motion if we didn't have friction. So net force depends only on the displacement from the center of oscillation. It does not depend on gravity. Okay, and we can treat it the same as horizontal simple harmonic motion since the restoring force is linear. So since restoring force is not constant, we talked about how the force changes as it gets farther and closer to the equilibrium point. We can't use our old kinematics equations. So they're, for this unit, we won't look at those really at all. Okay, and now what changes the simple harmonic motion? So the period in simple harmonic motion only depends on the mass and the spring constant. It does not depend on the amplitude. Okay, so let's take a moment. I'll write the equation down. So period, we can calculate the period is equal to 2 pi. Again, this will be familiar if you have studied this in math, times the square root of mass over your spring constant. So it's not dependent on anything but mass and spring constant. So to see this, let's go back and take a look, a quick look, at our simulation. So we go here. So I'm going to take this movable line here and set it at 40. And I'll take a stopwatch. So let's see how many cycles this thing will do. So I'm going to count 5 cycles. I'm going to start the stopwatch, count 5 cycles of oscillation. So we're going to pull it to 40. Okay, when it gets to the bottom, I'll start the timer, and then going up and back down is considered 1 cycle. And let's see how long it takes. So 1, 2, 3, 4, 5. Now again, the more cycles I let it take, the more my error will be reduced, my reaction time. But we got about 4.41 cycles. So let's see what happens then if we change the amplitude. let's, instead of 40, so that was 20 away from our equilibrium, let's go to 60 away from our equilibrium. Let's start our spring here. So same thing again, so 4.41 was at 40, that's how many seconds it took to complete 5 cycles. 1, 2, 3, 4, 5. So 4.38, almost the exact same time. So within my reaction, we can consider that the identical time. So even though we change the amplitude, it doesn't matter for the spring, okay, for the period of the spring. You can even shrink it if you want. Look, I'll just stretch it a tiny little bit. We can do the same thing. 1, 2, 3, 4, 5, 4.41. Okay, so this does not, the amplitude does not change the period at all. Now let's see what does change the period. So there's two things we can change here. We can change the mass. I'll get rid, since we don't need this red line anymore, since we know that the period has no effect. So let's double the mass. How does this affect the period? So again, we'll count. So first we had 4.41, so we've doubled the mass. 1, 2, 3, 4, 5. So 6.33. So it's increased the amount of time that it takes to do the same number of oscillations. Okay, so changing the mass increases the period. Let's go back. So let's go back to our 100 mass. And now let's increase our spring constant instead. So we'll make that larger. Let's make it as large as it go. And we'll bring it down. 1, 2, 3, 4, 5. So 2.86. We've almost halved our original time value of 4.4 seconds by increasing the spring constant. So an increase in the spring constant actually decreases our period. Okay, let's go back for a second and back to our original position here. What happens when we play with gravity? So remember our original period of the spring, right? Well, so we'll switch it to Jupiter. Our original period of the spring was 4.41 seconds. So let's pull it down. Let's do calculation. We have the spring constant set to what it was before. 1, 2, 3, 4, 5. So pretty much the exact same as what it would be on Earth. So gravity, like we saw when we just did that derivation a minute ago, gravity has no effect on the period of a spring. So you could actually, for example, build a clock out of a spring if you wanted to hold this. If you knew exactly how to make one oscillation take 1 second, the spring constant that you needed for one oscillation to take 1 second, you could make a clock. Okay, and you could bring this clock anywhere in the universe where their gravity exists, and you could, well actually, no, it would work in space too, because we can still stretch a spring even without gravity. So you can literally bring this clock anywhere in the universe, and it would bounce up and down 1 time per second. That's kind of neat. All right, so back to our equations. So we'll take a look at this first example. So spring has a spring constant of 43.2 newtons per meter. If a 135 gram mass is placed on it and made to vibrate, what will the frequency of vibration be? So our spring constant, okay, 43.2 newtons per meter. Our mass that we're hanging and oscillating is 0.135 kilograms. And we need to find the frequency of oscillation. So we can start, we can't find the frequency directly, but we can find the period. We know is 2 pi times the square root of mass over k. 2 pi times the square root of 0.135 divided by 43.2, and that gives us a period of 0.351 seconds. The frequency then is equal to 1 over the period, 1 over 0.351, or 2.85 hertz. So what this means is that in 1 second, this spring oscillates 2.85 times, or we can look at the period which says that it oscillates once every 0.351 seconds. So again, similar between frequency and period, but just slightly different interpretation of our system. Okay, we'll try one last practice problem. So when an 80 kilogram person climbs into a 1,100 kilogram car, the car's springs compress vertically by 1.2 centimeters. What will be the frequency of vibration when the car hits a bump? All right, so let's start with a diagram. Here's my car, my spring on my car. So this is its initial zero equilibrium resting position, just with the car by itself, no one sitting in it. Okay. Then we have a person sit in the car, and they cause the equilibrium position to shift to a new equilibrium position. So your weight pushes the car down some amount, we'll call x naught, to go to our new equilibrium position. The car then hits a bump. So when it hits a bump, it will start to oscillate around this new equilibrium position up and down. Now remember, an important thing is this first part when the person sits in the car. The only thing causing this change in the compression here, this change in distance, is the weight of the person. Okay, that's the only thing changing that's causing it to compress. When it goes over the bump, however, when it starts oscillating, it's the whole car that's oscillating, not just the person. So the whole car is bouncing up and down. So in the first section, we just consider the mass of the person, but in the second section, we have to consider the mass of both together. Okay, so let's take all of our information. We have the mass of the person is 80 kilograms. The mass of the car is 1,100 kilograms. We know that the distance that the person made it move to its new equilibrium position is 1.2 centimeters, but we have to convert that to meters. And we're looking for, in the end, what is the frequency? Okay, so the first thing we can do, we need to find period to find frequency, and to find period, 2 pi, we have mass, but it's mass over our spring constant. So we have mass, but we need to find our spring constant. So first we can find our spring constant. Again, if we go back to when the person sat in the car, we have our equilibrium. Force of gravity of the person is equal to the spring force or the restoring force back up. So we get Fs is equal to Fg, Kx naught is equal to mass times gravity, K times 0.012 is equal to the mass. So we have 80 kilograms. That's the mass that caused it to move to this new equilibrium. It's 9.8. And we get a K of 65,000 newtons per meter. It's a large K, but we are dealing with the springs inside of a car. So we then take that K, fill it in to our period equation. Our mass now is 1,180 because everything is moving, not just the person. Okay, over 65,000. And we end up with a period of 0.85 seconds. So it's the time for one cycle. We want to find out, though, how many cycles per second. So we convert it to a frequency by doing 1 over the period, 1 over 0.85, and that's equal to 1.2 per seconds, or 1.2 hertz. Okay, so that brings us to the end of the first section on springs. So your homework is to complete the problems in section 2.4.1 online. You'll actually find this under the waves component at the bottom of the waves component. So again, 2.4.1 on springs.